Okay, I want you to try something for me right now. Just wherever you are, point up, easy. Now point left, done. Now point forward. You've just covered the X, Y, and Z axes, height, width, and depth. Now here's the challenge. I want you to point in the fourth direction. Not diagonal, not time, but a literal fourth spatial direction that's, 90 degrees perpendicular to the other three.
And unless you are currently existing as a hyperdimensional being, or maybe a very specific kind of theoretical mathematician, your brain just hit a hard wall. You physically can't do it.
That wall is exactly where we're living today. We're diving into a concept that feels like pure sci-fi, but is actually the backbone of modern theoretical physics.
We're talking about the fourth dimension and, potentially the fifth, sixth, all the way up to the 11th.
It's a wild ride.
Yeah.
And we're going to look at why our brains are essentially trapped in this 3D interface, giving us a very limited render of reality.
And we're not just looking at the math. We've got a really interesting stack of sources today. It ranges from hard physics papers from CERN to string theory breakdowns. And then it pivots hard into, of all things, Victorian literature and philosophical essays on perception.
Which sounds like a strange mix, but you really have to, don't you? You can't talk about the fourth dimension without crashing hard science into pure imagination.
You really can't. It's necessary.
Exactly. So the mission today is to figure out what a dimension actually is, why physicists are so convinced there are these invisible ones curled up all around us. And this is the part I love, how just trying to visualize them might actually make us more humble human beings.
It's the ultimate exercise in perspective. It really is.
But let's be real. Even for people who love science, this stuff can be a headache.
Yeah.
I mean, trying to visualize a tesseract is enough to make you dizzy.
Well, that's a feature, not a bug. Our senses, they evolved to keep us alive in a 3D environment, Hunting, gathering, not falling off cliffs.
Right.
They weren't designed to perceive the absolute truth of the universe. We see a user interface. Math is the only way we have to peek behind the globe.
So let's peek behind it. We all know the basic geometry, ladder point, line, plane, solid. We don't need to rehash middle school math. But one of our key sources, Edwin Abbott's novella Flatland, uses that ladder to just absolutely dismantle your sense of reality.
It really is the Bible for this topic, even though it was written way back in 1884. Abbott sets up this 2D world, Flatland, populated by geometric shapes. And the protagonist, who is called a square, has a very specific perception problem.
Right, because he's flat. He has length and width, but zero height. So when he looks at his friend's triangles, circles, he doesn't see shapes.
No, he just sees lines.
Just lines.
The source uses that great penny analogy. If you put a penny on a table and look at it from above, you see a circle. That's the 3D view. But if you lower your eye level to the table surface,
it becomes a line.
It becomes a straight line. That's the square's entire existence. He can tell people apart by how bright or dim the line is, which tells him about depth.
And the horror starts when he gets a visitor. A seer from Spaceland, from our 3D world, decides to pass through Flatland.
This is the crucial moment for getting your head around dimensions. To the square, the sphere. It isn't a solid object. It just appears as a circle that magically pops into existence. Grows larger, shrinks, and then just vanishes.
It's a ghost.
To him, yes. He's seeing a 2D slice of a 3D object. And the sphere tries to explain the concept to Up, but the square thinks he's insane.
Of course.
Up is not a direction in his universe. It's nonsense.
Until the sphere finally snaps, grabs the square, and physically lifts him off the page into Spaceland.
And suddenly the square can see the insides of his friends. He can see his locked house is actually open from above. His entire worldview just shatters.
And this is where the physicists in our source stack start pointing their fingers right at us. They're saying, hey, you are the square.
We are absolutely the square. If a 4D object passed through this room right now, we wouldn't see some kind of hypershape. We'd see a 3D object, maybe a sphere or a blob that appears out of thin air, morphs and twists in ways that defy physics and then vanishes. We are just viewing the 3D slice of a higher reality.
That is so unsettling. It's the idea that there's a monster right next to you, but because it's slightly up in the fourth dimension, you just can't see it.
Up in a direction you can't even point to.
Now, we need to make a distinction here, because when I hear fourth dimension, I usually think of Einstein. Time. But the string theorists are talking about something else.
This is a huge point of confusion. In general relativity, yes, time is the fourth dimension. We live in 3D space and we move forward through time, and that creates a space-time block.
Right.
But the sources we're looking at today, specifically on string theory and geometry, they're proposing a fourth spatial dimension. Another where? not a when.
Which brings us to the tesseract. And I don't mean the blue cube from the Avengers.
Huh, no. Though the concept is related, a tesseract or a hypercube is the 4D equivalent of a cube. Think of it like this. A 3D cube casts a shadow on a 2D floor, right?
Sure, a flat square.
Exactly. Well, a 4D tesseract casts a 3D shadow. That shadow is what we call a tesseract in our world. You know, that cube inside another cube thing. But that's just the projection. The real object is much more complex.
I was reading that paper by Charlize Edwards, and she talks about how relativity and perception would work.
Yeah.
And the simultaneity concept she brings up is what really freaked me out.
It's the logical next step from the flatland experience. When you look at a square on a page, you see its borders, but you also see its insides all at once. You're above it.
So a 4D being.
A 4D being looking at you right now doesn't just see your skin. They see your skin, your heart, your brain, your stomach, and the chair behind you all simultaneously.
Wow.
They don't need x-rays. To them, you are completely open from that fourth direction.
That is incredibly invasive.
It gets weirder. If they are viewing the entire space-time block from that higher dimension, they might perceive your birth, your life, and your death as a single static object.
What, like a movie film strip?
Or like seeing a snake, the tail is your birth, the head is your death, and they see the whole creature at once.
Okay, that shakes my sense of free will a little bit. But let's ground this. We can't see these dimensions. We can't point to them. Why are physicists, people who deal in hard data, so convinced they exist? Why isn't 3D enough?
Because the math breaks without them.
Breaks how?
When you try to reconcile quantum mechanics, the very small, with general relativity, the very big, the equations just don't work in 3D. You end up with nonsensical results, like probabilities that are negative number.
You can't have a negative 50% chance of something happening.
Exactly, it's a red flag. But if you add extra dimensions, more degrees of freedom where particles can vibrate, the math suddenly snaps into place. String theory requires 10 dimensions to be consistent. M theory needs 11.
So they sort of invented dimensions to save the equation.
In a sense, yes, but it solves real-world mysteries, and the biggest one is called the hierarchy problem.
This is the why is gravity so weak?
Right. And it sounds counterintuitive because gravity keeps us on the planet, but just look at a fridge magnet. That little piece of metal, using the electromagnetic force, can cling to the fridge against the gravitational pull of the entire Earth.
The whole planet is pulling down, and this tiny magnet just wins.
Easily. Gravity is roughly 10 to the power of 32 times weaker than the other forces. It's absurdly weak. And that doesn't make any sense unless
Unless it's leaking.
That's the leading theory from our CERN source. Imagine the universe is like a membrane, a brain. The electromagnetic force is trapped on this brain, like a string tied to a surface. It can't go anywhere else. That's why it feels strong to us.
But gravity.
Gravity might be a closed string, a loop. It isn't attached, so it's free to drift off the brain and leak into those extra dimensions. What we feel as gravity is just a tiny fraction that happens to stay behind.
That is such a cool concept. Gravity is weak because it's the only force that's like exploring the multiverse. But if these dimensions are real, where are they hiding? Why don't I lose my car keys in the fourth dimension?
Well, maybe you are. But the consensus is a concept called compactification.
This is the idea that they're all curled up, right?
Yes. The CERN source uses the tightrope analogy, which I love, but I think a garden hose makes it even clearer. Imagine you're looking at a garden hose from way up in the stands of a football field. Just looks like a 1D line.
Right, you can only go forward or backward on it.
But if you're an ant on that hose, you realize there's a second dimension. You can walk around the circumference of the hose. That dimension is real, it's there, but it's compactified. It's curled up so small that from the stands you can't see it.
So we are the people in the stands, and the subatomic particles are the ants.
Exactly. Physicists believe that at every single point in our 3D space, there are these tiny, curled-up six-dimensional shapes. We're just too big to notice them, but particles might be traveling through them constantly.
So how do we prove it?
Well,
We can't shrink ourselves down to ant size.
we use brute force. We use the Large Hadron Collider, the LHC. We smash protons together at near light speed, and we treat the debris like a crime scene.
The crime scene, I like that. So what's a body we're looking for?
Missing momentum. There's a strict law in physics. Conservation of energy. If you smash two particles together with a certain amount of energy, all the debris that comes out has to equal that same amount of energy. The books have to balance.
And if they don't?
If we create a collision and the detectors show missing energy, like a spark just vanished into thin air, It implies that a particle, maybe a graviton, escaped our 3D brain and shot off into a higher
And
dimension.
stole the energy and ran.
That's the smoking gun. That, or finding what are called Kaluza-Klein states.
This was the part about echoes, right?
Yes. Think of a guitar string. You pluck it, it vibrates. If that string can also vibrate in a fourth dimension, it gets extra momentum. In our world, that extra momentum manifests as mass, so we might find a heavy version of a standard particle.
Like a Z boson that's 100 times heavier than it should be.
Exactly. It's the same particle, it's just buzzing in a direction we can't see. And that vibration looks like a heavy 3D particle to us.
I want to pause here because whenever we talk about extra dimensions, people's minds go to parallel universes. I know I confuse them. Are we talking about the multiverse here?
I'm so glad you asked, because pop culture just mashes these together constantly. They're very different things.
Okay.
A parallel universe, like in the many worlds interpretation, is usually thought of as a separate bubble. It's light years away, or it's completely disconnected from our own.
So that's like a different house down the street.
Or a different city entirely. But extra dimensions are here, right now. They are part of the fabric of this room.
So it's not a house down the street. It's finding out your own house has a secret basement you never knew about.
That is the perfect distinction. It's not elsewhere. It's more of here. It's an expansion of our local reality, interwoven with the very space you're occupying right now.
That somehow makes it infinitely more eerie to me. Now, we've smashed the particles, we've done the geometry, but I want to loop back to where we started, to flat land. Because we have this essay by Jacob Honshu that argues this isn't just about physics, it's about sociology.
This is the so what of the whole deep dive, really. Abbott wasn't just writing a math textbook. He was satirizing Victorian social hierarchy. But more than that, he was critiquing the human arrogance of certainty.
The mental chains.
Right. In the book, the square visits Pointland. The king of Pointland is just a single dot. He can't move, he has no dimensions, but he talks to himself constantly, praising himself as the all in all.
He thinks he's the entire universe.
Because he literally cannot conceive of anything outside his own point of view. But then the square visits Lineland. The king there sees the world as just a line. When the square tries to move left or right, the king doesn't just get confused, he gets angry. He calls it heresy.
He wants to execute him.
He wants to execute the square for suggesting a reality that contradicts his own.
And the irony, of course, is that when the square gets to Spaceland and tells the sphere, hey, maybe there's a fourth dimension, the sphere does the exact same thing to him.
Yes. He tells him to shut up. It's the cycle of dogma. We all think our dimension, our cultural perspective, our political bubble, our historical era is the spaceland. We think we see the whole truth. But the math suggests we are likely just as blind as the king of Lineland.
It connects right back to Plato's allegory of the cave, doesn't it? We're watching shadows on the wall and fighting over what they mean, completely unaware of the objects casting them.
It forces intellectual humility. If you accept the possibility of a fourth dimension, you have to accept that your sensory input is limited. You have to admit that reality is a construct. It suggests that when you disagree with someone, maybe they aren't just wrong. Maybe they're just looking at the object from a different coordinate in a higher dimension.
That's a powerful tool for modern life. We're all just 2D squares screaming at each other about lines, not realizing we're all part of a much bigger cube.
Exactly. Navigating the world with that knowledge, that there are directions you cannot point to, but that exist nonetheless, is a profound shift in mindset.
So we've gone from the horror of a 2D ghost to gravity leaking out of the universe to the humility of realizing we're all trapped in a limited interface.
We've covered some ground.
But I want to leave the listener with that one final haunting thought we touched on earlier, the shadow concept.
It is the thought that keeps me up at night.
Walk us through it one last time.
Okay. You are a 3D object. When the sun hits you, you cast a 2D shadow on the ground. That shadow is a projection of you. It moves when you move, but it's flat. It lacks your mind, your complexity. It's a simplified, lower dimensional version of you.
Right.
Well, if string theory is right, if there really are 10 or 11 dimensions, who is to say we aren't the shadows?
That's the kicker.
What if your 3D body, this thing you think is you, is just the shadow cast by a much more complex 4D or 5D entity that is the real you, a version of you that exists outside of time that is fully complete?
We might just be the flat projections on the floor of a higher reality.
We might be.
Well, on that absolute existential crisis of a note, we are going to sign off. Try not to trip over any extra dimensions on your way out. Thanks for listening to The Deep Dive.